By popular demand, I will be showing you where the developers of TES Oblivion Remake absolutely butchered GPU optimization. Not only will I show exact frame outliers, you're also going to learn about specific GPU functionality that exists to maximize performance, excellent data exposing terrible default behavior in UE5 to further validate market complaints against the engine, and I'll share extremely important data that debunks Epic's own educators and their long-standing advice so that you can understand why Nanite is so fundamentally anti-performance. This is the area we'll be analyzing, and I'd like to thank Nick Tech for helping us out with providing a save game based on where he found performance issues. This really helped us get our video out faster, so make sure to go subscribe or support their channel. Next time you find a specific game area with poor performance, make sure to keep a save game and send it to us so we can check it out. As always, we're running the game on a desktop 12GB 3060, and we wanted to analyze the bare minimum settings, and these were the lowest settings that enabled Lumen, which this game was clearly built around. And this time we're leaving the default TAA settings on so that people can get a really good sense of how destructive this AA method is. This entire bar chart displays all GPU elements that took processing time to generate the frame, but I'll go ahead and change the view mode so that empty draws don't waste our view space. The frame starts off with around 55 compute shaders related to Unreal Skin caching system, which forces the GPU to process in-game animations. In-game animations alone take around 1 millisecond. This next portion of process is a lot of data, but it's all mostly related to GPU instancing, virtual shadow map information, and global distance field systems. This single draw accesses several textures to shade 3 68x68 textures that are used as inputs in the next compute shader that write this information into two 5100x5100 BC3 textures, which take up around 50 to 40 megabytes of information. These two BC3 textures are only used twice in the pipeline for a single asset in the frame. Even if I brighten the draw, you probably won't even notice the asset until I darken the rest of the image. Only 5,000 pixels were rendered for the object, yet it cost 80 microseconds, or almost 1/10 of a millisecond. To understand how poor this is, optimized deferred draws can achieve a 1 microsecond per 1,000 pixels rendered ratio, as showcased in optimized titles we've analyzed on this channel. Tiny draws that render maybe 1 to 2 pixels, or the initial draw cost can range from 9 to 15 microseconds. If you're new to the channel, we showed how the CryEngine version used for KCD2 consistently had the lowest initial draw cost for deferred objects. After a few render target clears and a few tiny draws, the GPU begins processing the non-Nanite prepass. But here's the thing. A prepass is supposed to be fast because it only renders geometric information, but the dense wireframe and almost 600,000 vertex as input and just the outlier suggests quad utilization was hurting the prepass efficiency. The non-outliers have the same inefficiencies, just more spread across the frame. Unlike a regular depth prepass that's purely vertex shader driven, this prepass uses pixel shaders to also write object velocities. This is the default behavior in many if not all Unreal Engine versions, when velocity should only be calculated during the base pass, where all your other pixel shaders execute. Assuming we need motion vectors for all geometry, if we process this compiled example with geometry timings with Unreal's default behavior, nothing seems out of the ordinary. But if we group our pixel shaders together, it only increases the base pass cost by 1.6%. The prepass, on the other hand, becomes fully vertex-driven, granting a 28.5% increase in performance. This next portion of draws references a high Z containing the full depth of the last frame, so that current frame Nanite clusters can be culled. Nanite transforms regular meshes into clusters. These clusters are then swapped out with smaller clusters when the object becomes smaller on screen, allowing the detailed clusters to stream out of VRAM and vice versa. These clusters are rendered into a visibility buffer for reasons I'll explain in just a few moments. But the main thing you need to know about it is that it's a lot like that velocity prepass in the sense that both calculate mesh data without textures. So the idea is that the shading cost is supposed to be more similar to a vertex depth prepass than material shaded objects. But Nanite has two other huge issues we're going to explore. Nanite uses a software triangle rasterizer for small triangles to avoid quad bottlenecks, but this means it relies on cluster bounds to cull other clusters. When this cluster-dependent system fails, and it does in almost every scenario, unseen geometry is processed. But the software rasterizer doesn't have access to hardware depth testing or Z-testing. To explain hardware Z-testing, we'll render a rectangle with 10,000 triangles and then measure the cost of rendering a larger copy behind it. Here's the quad utilization, and the total cost of rendering that first rectangle cost around 0.08 milliseconds. And when we render a larger copy behind it, its cost is only 0.2 milliseconds. When the first rectangle was processed, it was shaded at a somewhat slow rate due to the amount of pixels it was invoked to shade, and it was further slowed down by the poor quad topology. When the second triangle was processed, a fixed hardware function on the GPU continuously rejected all 2 million invocations for that new rectangle by testing if the new vertex positions were behind any depth values currently rendered. This is z-testing, a very fast feature that gets applied to all buffers, which is why we do depth prepassing and front-to-back rendering. With Nanite, when a cluster with small triangles are detected, it's sent to the software rasterizer, as you can see highlighted in blue. The hardware shading uses mesh shaders, but let me quickly display the z-testing issues with Nanite. We can establish our initial Visbuffer cost at 0.35 milliseconds, and the 10,000 triangled mesh is a perfect density where hardware mesh shading is still used. The first rectangle is rendered 2 times slower at a 0.16 millisecond cost. Drawing the larger rectangle in the background like before costs 0.06 milliseconds, and provides us with a cost of full screen 2x overdraw for Nanite mesh shading, meaning z-testing is either non-existent or 3 times less efficient. In order to measure software rasterization, we need to bake displacement to get the triangle small enough to enable software shading. And we also need to make the surface less smooth so that Nanite wouldn't auto-collapse the details in a way that wouldn't apply to other dense meshes. Shading this mesh takes 1.07 milliseconds. This should display how slow software shading can be even in a scenario where the bare minimum pixel density is enabling software shading. When we measure the cost of pixel overdraw though, the occluded rendering takes 0.60 milliseconds, which makes non-visible geo 2,900% less efficient than optimized z-testing. We have 2 major conclusions to cover with this data. First, this data should make clear why it's so ridiculous that Epic Games speakers who are supposed to give optimization advice for Nanite are telling developers not to let visibility overdraw raise alarms for performance. Overdraw literally means wasted processing on the GPU. But Matt Ostale in this video says, "I prefer if you didn't," when speaking about object inspection regarding findings in overdraw. It's like having a cluster of pimples on your face and someone telling you don't put zip cream there because it's too much effort. It only looks like a skin problem, but I prefer if you didn't look at it like that. Then proceeds to tell developers to avoid over-optimizing. So some of you might ask yourselves, is there such a thing as over-optimization? And the answer is no, not really. But there is such a thing as poorly executed optimization that is work or effort heavy because missing workflows or current software don't facilitate easy ways to optimize. And that is why we advocate for easy or automated optimization tools. In this video, Matt Ostale falsely claims that Nanite is a faster rendering pipeline, when that is only true if the content's initial optimization is neglected or butchered. This is also the second time an official Epic employee has recommended Nanite on low poly content, but contradicts Brian Karas's, the inventor of Nanite, reasons on why it should be used with low poly content. But to bring clarity here, they are both wrong for different reasons. On one hand, Ostale is saying use Nanite because it's faster and saves memory, and Karas is saying use Nanite even though it's slower and saves memory. What a more accurate statement is that it's slower, and any memory gains are worthless if the performance is poor. This is why Nanite is continuously proven unfit for games. The second thing I want to address is the fact that I was stacking the layers closely to measure pixel overdraw timings, and many people will bring up how that's an official bad practice for Nanite performance, because it messes up the cluster culling. But that's the whole point. If you add up the timings for the hardware shaded Visbuffer and include the initial cost, it ends up being exactly what the Visbuffer timing in my last video's example Nanite scene, where overdraw was pretty mild and mostly rendered by mesh shaders instead of the slow compute software rasterizer. And what you're supposed to understand here is that even in a well-optimized Nanite scene, cluster culling will always have leaks and guaranteed error, which results in a cumulative overdraw that ends up being equivalent to shading the Visbuffer twice, like these tests, which is determined by the scene's main raster method. Speaking of raster modes, this data shows how poor Nanite's main optimization view is. The heat map logic for Nanite's overdraw view mode will highlight 2 layers of mesh shader rendered objects, but if there's software compute shader rasterization with no overdraw, that will take 3 times longer to render than both of these layers. But developers won't see that. The heat map must multiply pixel values based on whether or not it was mesh shaded or compute shaded. Compute shading should either appear brighter or even color tinted. The hardware software view mode is not heat map driven and is hidden behind a console command. During the writing phase of this video's production, one of my colleagues asked me, "Do you think Matt Ostale understands Nanite as well as you do?" I took a few moments to consider this so I could answer with precision. And I said, no. Absolutely he does not. He doesn't seem to fully understand what he's talking about, because Ozdelay constantly echoes incomplete Nanite advice. For example, in this video, he clumsily skims over the raster view mode with no apparent cognition of its importance. He also says the hardware raster path for Nanite uses traditional rendering, when traditional rendering uses vertex shaders, while Nanite uses mesh shaders, which have been documented over and over again by several developers to be slower than optimized vertex shader scenes. He was given the console command to give him an unearned aura of wisdom. His solution to Nanite overdraw is even triangle distribution, which does not work for a lot of content because Nanite automatically rids small clusters if flat surfaces are detected. Nanite automatically collapses those unless the surface has microbumps, which kicks in the software rasterizer, which is more expensive than the mesh shader overdraw that he is teaching how to prevent. This is a classic snake eating its own tail. Now that we have a better understanding of Visbuffer rendering, let's analyze what this highlighted portion rendered. We can analyze the Visbuffer with a color modified depth or with one of the ID channels. For now, I'll stick with one of the ID channels. This first portion of draws are mostly rendered with mesh shaders, and the compute shader software rasterizer was probably invoked for micropolygon foliage. The next draw shades all the new objects with the software rasterizer, and the cost is made worse since the geometry holes break the cluster bounds required for culling. From this point, the draws only use software raster via compute shader. Analyzing the frame contents of this draw should make clear how sorting isn't driven from front to back rendering, which is causing a lot of waste. The next draw only uses a small amount of compute shading, but I wasn't able to find where on the frame it shaded, but it references multiple textures, which is always terrible for a prepass. This draw is one out of the 2 times that one of these 5100 by 5100 textures are accessed. This next batch of draws mainly shade micropoly leaves, but their movement is evaluated in the shader, and this requires access to 2 textures, which is comedic considering one of the reasons micropolygon leaves are suggested for Nanite is to avoid drawing textures in the Visbuffer. Draw A32 takes up substantial amount of time, yet nothing visible renders in the buffer. All we know is that it was some kind of masked foliage content. More micropoly leaves and masked foliage are rendered with those animation textures we viewed earlier. Draw 961 is quite odd. It only renders the tent meshes, but somehow the developers tied multiple textures to the draw depth. These textures are also pretty big and don't contain tessellation maps or depth cutouts for masked evaluation. The next 2 outliers render micropolygon grass using one animation-related texture. The GPU then combines the Visbuffer depth and the non-nanite depth to make a singular high Z, so that the GPU can start processing mesh clusters it knows will be visible for this frame. The bigger operations in this next batch of draws sort some of the visibility buffer data into different formats for later operations, and it evaluates the static velocity of objects inside the visibility buffer beyond a certain distance, and writes that data into a velocity buffer. The smaller draws are made up of occlusion queries. These draws process a lot of high-resolution textures and update 4 512 by 512 lumen related textures. Some additional nanite cluster processing is initiated, and then 1 or 2 decals are written to 4 deferred decal buffers. In Frostbite and in CryEngine, the decal was a mesh that was rendered on top of already rendered geometry, except without any depth information. In Unreal, you don't have access to an efficient mesh cutout. Masked textures are instead projected from a cube, but it's rendered inside dedicated buffers before geometry is processed, and this requires a horribly inefficient full prepass. Now, many complacent devs and Unreal defenders will say, but Epic gives the option to render without a prepass and dedicated debuffers. The problem still remains that it's the default engine behavior, which AAA never fixes 90% of the time, and Epic made this the default because without that option enabled, decals won't work with Epic's poorly implemented lighting techniques. These are core issues in modern rendering that nobody else is trying to raise awareness about. So make sure to hit that subscribe button if you haven't already to support our efforts. The next step in the pipeline is the Basspass, where materials are evaluated. Non-nanite meshes are rendered first to the geometry buffers. Character draws are slowed down by topology and high texture counts, so that shouldn't be present. Other faster draws only use a BC7 and BC1 texture. The GPU then gets ready to evaluate the nanite visibility buffer. To quickly explain what happens next, we need to understand what a visibility buffer is. Normally, a mesh is processed by a programmable vertex shader, which provides the geometric context for the pixel shader, which usually fetches data like the related textures. The pixel shader evaluates the results on a buffer, but pixel shaders aren't limited to processing conventional vertex structures. You can draw 2 triangles, better known as a full-screen quad, over any pipeline buffer, and feed any inputs like additional lighting buffers, and shade that vertex content with custom pixel shader logic. Again, full screen quad shading is done for several rendering techniques. At the time, pre-passing depth for immediate Z testing was crucial for forward rendering performance, but reprocessing meshes in the pipeline wasn't mixing well with integrated graphics. So the idea of the visibility buffer was to extend the depth information into 2D representation of mesh triangles, where just enough data could be reconstructed by pixel or compute shaders, so that those textured materials could be evaluated like normal. The first Nanite draw uses 10 draw unique textures, too many to go over one by one, but obviously this was a large reason why this draw was shaded more than 50% slower than the normal optimized ratio. Notice that Nanite uses a tiled vertex structure instead of a full screen quad. The rocks in-game aren't even impressive to warrant such a pathetic cost. The next outlier draw is basically the same story, and less prevalent materials are also accessing 8 to 10 textures, making their initial cost higher than normal. The biggest draw shades the terrain, which accesses several high-resolution textures, and performance is around 5 times slower than 8th generation terrain rendering. The next outlier renders distant terrain with the same inefficiencies, and I'm going to go ahead and just highlight all the other outliers and display their normal output because we can't efficiently present the amount of bloated textures used in this single video. It's just too many to cover. Many draws like 2450 shaded the log using several high-resolution textures at once to process real-time texture blending instead of baking per-object textures like optimized games that efficiently manage memory with bitmap streaming. The foliage and trees also access overly high-resolution leaf and animation textures. But all these outliers also access these giant atlas textures, which don't even seem related to Unreal's virtual texture system. The smaller Nanite draws access small bitmaps, averaging around 64 by 64 and lower, but still access a lot at a time, pushing the draw cost to that of around a PBR forward rendered draw, or even twice as much. This next portion starts with some processing related to virtual shadow maps and updating a distance field atlas. This portion initiates distance field traces, Lumen cache updates, and temporal and direct shading operations, which cost around 3.4 milliseconds. The next portion begins processing the virtual shadow map, which will rasterize the depth of many triangles that appeared in the visibility buffer, such as the animation movement textures and that really slow tent we saw earlier. This is all rendered inside 2 extremely large atlases. The main issue with VSMs other than poor performance is the way that they anti-alias with noise, promoting dependency on flawed TA. This and the fact that they rely on slow Nanite to function properly. This portion processes non-Nanite shadows followed by some data management. Then, Unreal's horribly noisy and poorly designed SSAO is processed. The smaller portion processes Lumen reflections at a half resolution at a fast speed because there aren't many surfaces below the roughness value of 0.4. The next portion writes 2 shadow masks. The bigger draw relates to the VSM shadow mask, and the smaller draw relates to the cloud shadow mask. Then, using a full screen quad, the GPU uses the G buffers and all indirect lighting related buffers as pixel shader input for evaluating skylighting in clouds, and then the buffer is further shaded by the main directional light in the next draw. Skin subsurface scattering is processed inside a half resolution texture, and then volumetric fog data is updated and accompanied by low resolution volumetric cloud shading. The low resolution subsurface scattering is then added to the lit frame, shortly followed by fog shading. Then, a few small dispatches process some unknown particle effect data. The main lit buffer is copied a few times without any telling context. Then this 0.3 millisecond dispatch computes TA while referencing the raw current frame, its motion vectors, and its depth, the last TA frame and its motion vectors, and the standalone TA frame before that one. This produces the current TA frame in a 540p variant. Here are some comparisons with TA off and on. The only reason why Epic's TA is so poor is because they are obsessed with abusing its unneeded flaws. Color grading and bloom related draws take 0.3 milliseconds, and the color graded image is written to another buffer with more color modification, but the buffer is specifically identified as an FSR buffer, even though FSR is disabled. The pipeline ends with UI draws completing the frame. Since Nanite rendering is a bit harsher on debugging tools, we're going to lay out some of the budget by disabling engine features one by one, and we can use screenshots to get the most accurate timings. The GPU frame usually takes 24 milliseconds to process, but after Nanite clusters are forced not to draw, we get a guaranteed performance gain for Nanite, but we run into a CPU bottleneck. This is when we can add our analysis data, including secondary analysis data, capturing the CPU bottleneck scenario, and this gives us a rough idea of the complete nanite timing, and we'll even take some off to give nanite a fair shot. Now we end up with the final timing within the average FPS. Now, one of the reasons I wanted to do an analysis of this title outside of popular demand for it was to showcase legitimate developer/studio faults that aren't related to the engine, which mostly revolved around the materials. But the developers author Foliage with micropoly over masked foliage because this is heavily promoted advice in the Unreal Engine community. It is because you would be drawing opacity textures in the visibility buffer with slow mesh shaders, and then redraw that texture in the Nanite Basspass. This was already an inefficiency in regular non-Nanite rendering with full pre-passing, and UE devs just started noticing the problem because Nanite was multiplying existing inefficiencies. But what I love about our first conclusion is that we've shown that software rasterizing a bunch of micropolygons with faulty cluster bounds is an extremely poor approach. And no, voxel garbage running at 800p on a PS5 is not going to be faster than optimized Basspass exclusive Foliage. Now let's go over the hypothetical where this studio baked and optimized their materials. That doesn't fix Unreal's low quality anti-aliasing, and there's nothing the developers could do right to get Lumen from not looking like a pathetic rendering glitch without TES. There is no right engine setting to fix Unreal's butchered implementation of Ben Studio's screen space shadows, and these are things that are not even fixed in 5.6. When this Paris demo hit the news, a lot of people, especially Unreal devs, became overwhelmingly optimistic to the point of complete delusion. Now this demo was produced by a third-party asset producer, but Epic Games during the state of Unreal specifically told people to test this demo, and we found that extremely suspicious, so we're going to go ahead and share what we found. On the Epic Scalability native 1080p on a desktop 12GB 3060, we can first detect a whopping 22% GPU performance increase in UE5.6. But both demos were using hardware Lumen, which was completely neglected performance and R&D-wise pre.5.6, so there was nowhere to go but up in performance. What Epic does not want reviewers to focus on is the fact that the hardware path was the only significantly optimized GPU engine feature because there is almost no performance increase when the software Lumen pipeline is used, which is what game developers actually use when targeting 60 FPS. Now you might try to see a glimmer of hope with that extra 2 FPS offered in 5.6, but if you inspect the scene, we can see that the 5.6 project conveniently does not render these frozen NPC models in multiple areas. We're not sure if this contributes to the 540 less draws in the 5.6 package, but we do know this is not an apples-to-apples engine comparison because of project alterations. The industry feedback to Epic was not make your smeary GI method more compatible with a slow information gathering method. The industry feedback was make your smeary, flickery, noisy GI method render faster without smearing, noise, or flickering like other GI methods. And even though the AO noise was somewhat mitigated, and actual CPU improvements do exist in 5.6, the Lumen team at Epic should be ashamed of their work. Lumen is a visual and performance embarrassment, and Lumen's team's complacency with software Lumen's quality drove them to waste development time and funds on research the game industry did not need. If you found this video educational, helpful, or even just interesting, make sure to hit that subscriber button, because the higher we get this number, the more it helps us strengthen the market for optimization and drives up the demand for better graphics. Because it takes several weeks for us to produce this kind of quality content, YouTube's revenue is not enough to sustain our efforts. So if you can, join our Patreon where you can get access to image comparisons and pipeline extracted frames. But if your budget is tight, we appreciate you just sharing our content on game/game dev subreddits, Discord channels, and social media at least 3 times, which will greatly help our revenue enough to keep us afloat. Thank you so much for your positive support and viewership, and see you in the next video.